Okay, so this is part 3 of the lecture 9 on text data with RNNs. And let me finish up with just talking a little bit about RNNs. So we spoke about RNNs and LSTMs last time. But now that we have these embeddings of these tokens, what we're going to imagine is that that is what our inputs are going to be. So in our LSTM, we will pass in one token at a time, or 2 tokens or something like that. But we'll have a sort of a fixed length vector that will get passed in, and we'll keep passing those in, and then the output, depending if it was a classifier, would just be a one-hot vector, or it could be, if it's a translation program, it could be another token, that another embedding token that'll come out, and then that'll get translated into a word. So that was the architecture we saw last time for LSTMs that have this carry kind of a memory, and an input stream and an output stream, and a bunch of these activations that forget and remember different parts of the carry, which has a certain dimensionality. So it could conceivably remember a bunch of tokens or some version of tokens. It's not literally looking at tokens. Now there's a bunch of architectures that people have been playing with and thinking about, and I didn't put in Mamba here, but Mamba is one of them. So the RNNs and the LSTMs, RNNs, these kind of models were sort of state of the art a little while ago, but then transformers became very popular. But transformers have their own issues. They end up having a very large number of parameters. They end up being pretty slow because they have to keep track of relationships between, like, arbitrary relationships between the beginning of the text and the end of the text. And in some ways, the RNNs can be more efficient about their representations and the parameters they have. So one of the models that people looked at was the idea that rather than have a carry, you can think of it as a neural Turing machine, that the memory is basically a tape, but it's a certain size, and you have an opportunity to write to that thing, and you also have an opportunity to read from it. So it's very similar to the LSTM, but it's modeled more on a Turing machine. And then I'll be talking about this more later, but one of the issues is that when you're parsing information, if we're trying to recognize a dog in an image, or a word, a concept, to translate it to something into French, we need to pay attention to multiple things, but we don't need to pay attention to the whole sentence, right? There are certain words in the sentence that are relevant for this translation, and we need to pay attention to those words. And so this came up with this idea of attention in 2015. So the idea is that you have your original representation, and if we're looking for some kind of a classification of this, maybe we have a way of figuring out what parts of the image are going to be important to look at in order to identify this, the object in this image, which is a cat, obviously. So our attention mechanism is something that we learn that it learns to just figure out where in the image it should be looking. And so let's say that this is the mask, and if you multiply this mask by this, it suppresses other parts of the image which are not really relevant for this classification. And so now, if this is the new representation, that means that the algorithm is not going to be confused by sort of this texture or this colors or any of these other, because that's being suppressed. And it's really just going to look at this part of the image and say, okay, that's a cat. So the idea is that you don't just have a memory, like a carry state or an input state that you're looking at, but you also have another vector, which is considered an attention vector. And each of these, whereas this memory state are different vectors that are representing, whatever words or whatever they're representing, different things. But the attention is just a weight. So this is just for each of these blocks that the memory is remembering. It's just remembering, like, these are zeros, and these are the two that you should be looking at now, and then these are all zeros. And then when it reads the result, to be paying attention to that, to do something with it, it weights them by this attention mechanism and then adds them up. So you can think of it as kind of like retrieval, right? So you've got this memory. If this were just a 1 and these were all zeros, then it would like go, okay, I need to retrieve this guy. But in this case, it's kind of a soft retrieval where it's retrieving multiple guys but taking their linear combination. They're average but weighted by this attention score. So self-attention is when we start to learn. Again, we could play that game where we try to remove some word and fill in the blanks. And we can look to see which words, if we're going to try to predict a word like station, station, which words would I need to know about? Which words are important within the sentence to figure out the prediction of station? And it turns out, right, that train is a really important word, right? The fact that it left maybe is not important at all because, whatever, the's appear all over the place. Left, train left is because the train left the station. So train left those are a little bit more important. And so in terms of if we've trained this on many, many, many sentences, in a sort of fill in the blank kind of a way, it will learn that if it's focused on station, then these other words are the words that are relevant to a relevant context for station. And that's called self-attention. It's the scores that this has of like the relevancy of other words so that it can pay attention to all of those other words when it's trying to do something with that token. Now as we read, right, imagine we're building, ChatGPT, you see the words kind of appearing one at a time. If we're doing a translation, things are happening one at a time. So what we'll tend to do is we'll mask words. So we'll look at the, and we'll try to figure out what other words are relevant for the. And there's only the, so there's no attention here. But then the next time we're looking at the FBI, and then there's only one other word, so the attention will go focus to the, because there's only two words here, and the is the other word. But then, when we get to is, FBI becomes the important word, and the is not that important because it's a sort of a stop word. So the model and attention part of the model will, and continuing in this, like we get to, let's say, criminal is a criminal. Those are the words that are like relating to criminal. The FBI is chasing a criminal on the run, and so forth. So as you move through, so here's a representation. We start off with some zeros, and then we have our input sequence, and we're doing a dot product and a softmax. So this is just a simple neural network to learn an attention. In practice, we're actually just going to use the PyTorch attention layers and things like this. But this is just to get some feeling for how these work. So you can think about the attention as being sort of they like to think of it as a query and key value. So you have your input, and you're looking at the pairwise scores, and then you sum those up to get the outputs. So this input is kind of a query, and this input is kind of a key. And then when you find which key it is, the result weights that particular word for the attention. So if you think about it as like retrieval, right? You say query dogs on the beach. In this image there are no dogs on the beach, but you get beach, right? The match for beach is very high, but the match for tree is there's a tree and there's a boat. These are the closest matches. But this is our phrase. So dogs on the beach. This image is got beach in it, but there's no trees or boats in here, so there's not an interesting key there. And then here, in this thing, the dogs in the beach match, and this one just the dog matches. So these are our keys. This is the query. This is the keys, and then the values are the images that we're trying to, and then we're going to weight the image by the key, by the query key combination, right? So here, this like beach part may be like bright and everything else will be dark, and then here the dog and the beach will be bright, and then here it's just a dog, and this is the closest match. So this is kind of the right one to be looking at. Now in an image, like here we have a beach and we have dogs, we have multiple things. So in reality, we need to pay attention to several things, and that's what multi-head attention is about. It's about having these queries that are looking for specific things. What part of the image is going to be relevant for me to make my decision? But because I'm looking at multiple objects, I'll have a separate ability to focus on certain parts of it and also focus on some other parts of it. And this is called multi-head attention. So if we had this is an example for captioning. So an attention mechanism is in this sort of classifier, incorporated in this classifier for captioning, right? And so when it's looking at when it's coming up with the word frisbee, the attention is actually, you can look at the attention model and it actually is the frisbee, right? Or when the dog, it's here, or the stop sign here. And, if you underline background, then this would be very bright. And just like we can stack RNNs, we can stack RNNs RNNs with attention. So instead of the inputs being the original tokens, they could be, this sort of the states of the previous levels. And this is just an example for like language translation, and also important for speech recognition. So what I'm going to encourage you guys to do is follow the example in the book and go through that, because I think that'll be pretty helpful in terms of like understanding how we would use these, and we'll talk more about attention when we get to transformers. Okay, so that's part 3, and that is the lecture for this week.